Next speaker, David Shoemaker of the MIT LIGO laboratory, giving a speech about neutron star mergers and heavy element production psi. No, I'm sorry. LIGO past and future observation of black hole and neutron star binaries.
Thank you. And thank you to the organizers of the conference, Rufini, Eventley, also Bob Jansen, for creating this wonderful environment for us to share our science. So I'm going to talk about LIGO. First thing I want to note is that the National Science Foundation of the United States has been a remarkable source of support for LIGO. We thank them for their vision. Other thing to note is that I'm speaking on behalf of the LIGO and Virgo scientific collaborations. It takes a lot of people to make things like this happen. So speaking of LIGO and Virgo, we work very closely together. We share instrumental ideas, coordination of runs, data, and publishing. And along that line, I'm going to say that we'll share the talks that I have today and Jo van den Brand has tomorrow between two different aspects of what we're doing. I'm going to spend my time talking about the detection and analysis principles, and so lead you through how we go from our raw strain data to confidence in our results. And then Jo tomorrow is going to have the fun part and is going to talk about the science that we can infer from our signals. And I have a lot to cover, and I hope I'll go quickly. I hope that will be okay with you all. So first off, what's our measurement technique? I think everyone in this audience is familiar with the notion that a propagating gravitational wave deforms space-time in a way that light travel time changes. For a periodic wave, it changes in a complementary fashion along two orthogonal directions. If you place a Michelson interferometer in the axis of that propagation, you'll get a differential phase shift, which will show up as a change in intensity at a light detector. So we have a transducer from gravitational wave strain to light intensity. The scary part is the magnitude of the signals that you have to detect if you want to detect signals frequently, and it's on the order of 10 to the minus 21. And with that, you have to have an extraordinary sensitivity, and it really is a challenging thing from the standpoint of fundamental physics to build an instrument that can make the detection. To put it in scale, my favorite analogy, but no one has an idea how big a proton is. The distance from here to Alpha Centauri is about 4 light years, and we could sense a fractional change in that distance of the thickness of a human hair if a gravitational wave were to pass between us and Alpha Centauri. It's really quite something. This is what our sensitivity curve looks like. This is strain on the vertical axis, frequency on the horizontal axis. It has this form of excess noise at low frequencies from seismic noise and related phenomena, and then a gentle rise at high frequency due to the quantum limit. We have a good idea of the basic fundamental noise limits. A lot of our time, of course, is spent fighting much more ordinary technical problems. But this gives you the overall scale. And if you look, I said we needed about 10 to the minus 21 to make detections. We've got about 10 to the minus 23 per root hertz. It works. So talking about what we are and where we are in terms of sensitivity, for the initial LIGO runs, I'm going to mostly focus on LIGO because that's my instrument. We were at this level of the green curve. For 01 and 02, the two runs that have resulted in the detections that you've heard about, we were about a factor of 3 better at high frequencies, and that, of course, makes a significant change. We measure amplitude. A factor of 3 change in our sensitivity makes a factor of 3 cubed in the number of sources within reach. What was really significant, though, was this factor of 100 improvement at low frequency, and that put these binary black holes into reach of our instrumentation. I have some fun because I was invited to speak here 3 years ago, and this was in August of 2015. And my final slide said that Einstein made his first predictions of gravitational waves in the paper with errors in 1916. And I thought we had a good chance of making a detection in 2016. Well, my prediction failed because it was only 1 month later, in 2015, that the first detection came along. We saw 2 black holes, some 36 and 29 solar masses, already an impressive and interesting result. It showed up so clearly in our data. This is just high-pass and low-pass filtered output from our strip chart recorder that measures gravitational wave strain. The 2 are slid by 6.9 milliseconds because the wave didn't come from directly overhead, but from the side. Now I'm going to spend most of my talk discussing how we go from that to a result. And so here's a bit of data analysis. So on the right-hand side, you see a flow chart, which is set up for 3 multiple detectors that talks about the various different stages. And I'm going to step through them one by one and give you a sense of what it's about. I'm only going to talk about binary inspirals here. There are very different approaches for different kinds of sources. We do assume that GR is correct for the search, but then we can look for mild deviations from GR. The ideal detector noise would be stationary, Gaussian, and uncorrelated between the 2 detectors. Our data are none of those things, or at least they're only approximation to it. And a lot of what we do is a process to bring us back to a point where we could make confident claims about detection despite the defects in our data. You can find more information, you can find more information if you're interested at our open data site. In particular, there was a workshop held there, and there's a series of instructional materials that could be interesting to learn more about the process. So the first step in our process is to form an estimate of the noise in the system, and to do that, we take Fourier transforms of our noise output. To do that, we use the discrete Fourier transform. It's, of course, not designed for, it's designed for data which are periodic. Our data are not periodic. It's a continuous stream. It's not like a look around the sphere of the Earth. And so we window our data to remove end effects in that Fourier transform. And in so doing, we move from this sort of a spectrum of the phase as a function of time to one which looks appropriately random. So this is one of the first steps in bringing our data from its rather non-Gaussian, non-stationary, non-perfect state to one which is easier to deal with for the data analysis. Then we have to make a set of templates. We assume in this search that we're looking for binary inspirals, that GR is an accurate description of it. So we make a series of different templates for different masses. Here, for instance, you see on mass 1 and mass 2, these 2 ranges here, the 250,000 templates that we develop. And we pass every bit of data over all 250,000 of those templates to see if any one of them might be excited. We remove clearly defective data. Here, the Livingston output was quite continuous in this short segment of data, but in Hanford, there were several dropouts, and these can be due to either mild earthquakes, there can be a technical noise that causes a saturation of electronics or so, and those are excised from the data, so we don't waste any time analyzing them. Then we form a matched filter. This is really a key point in the overall process. We have our signal, which is embedded somewhere in our strain data set, and we have our set of waveform filters. In the frequency space, we Fourier transform both of those. We make an estimate of the level of probability that our signal is sitting in, that our template is sitting in our signal, but we normalize to the noise power spectral density. This is a crucial step because our data are not, in fact, at all stationary. Our data are not white. Here's an idea of what the data look like. You've already seen it. It has excesses at low frequency and also at higher frequencies. But there are also many line features here. We understand those lines. They come from power lines. They come from intentionally impressed calibration lines. They come from the thermal excitation of the fibers that suspend these masses. So the key thing is to suppress those in our estimate of the importance of a signal. And we do that because this power spectrum density appears in the denominator. And to give you a somewhat more visual sense of that, I just took that curve, flipped it over, and squared it to show you, give you a sense of the suppression by orders of magnitude of all of those line features. That's a very important part of our process. Then we also have non-stationary noise, which doesn't cause the interferometer to lose lock or for us to snip out data, but still could mimic a gravitational wave signal and must be removed. So we require that the signal is seen in multiple detectors, that the relative phase and amplitude is consistent with an astrophysical source. The signal morphology has to be the same between the 2 observatories. We have to be consistent signal model and observed data. We have to exclude then these glitches. And the first thing we do is we look in some 200,000 auxiliary channels to find if the transfer function from those channel detectors to our gravitational wave strain shows that the gravitational wave strain signal was just due to some kind of noise. Someone claps their hands in the experimental space, that would make a plot like the one I show here. Ooh, interesting. I wonder if that'll happen if I clap my hands again. Let me talk a bit more, though, about how we exclude these things. Now, you'll see that here you see a black line. This is actually a template that was excited by that glitch. I should have turned off my Wi-Fi, I guess. And so we have to somehow prevent the system from recognizing that glitch as an in-spiral. What we do is we cut the signal into bits and pieces, and we require that each section of that resemble a template for the same astrophysical phenomenon. And we form a chi-squared test with that measure to ensure that we're not fooled by this sort of glitch. We're ready to estimate the significance with our data, which of course are not stationary, not Gaussian, and so forth and so on. How do we look off source? What we do is we move to times which are nearby our event moment, but not on the event moment, and we slide the data from the 2 or 3 or however many detectors so that it be impossible that a gravitational wave be responsible in the 2 different detectors. Between the 2 LIGO sites, it takes 10 milliseconds for a photon to travel, or a graviton. And so what we do is to slide the data by more than 10 milliseconds and look for signals. Anytime we see a signal, of course, that it contributes to a larger background. By doing hundreds of thousands of these time slides, we can form a very accurate estimate of the background as polluted by our defective instrumental noise. And in that way, we can make an estimate of the significance of our signal in the context of our actual noise. And in that process, come up with a good number. And then, of course, we want to test the system. We inject many signals via software and determine that our pipelines can actually detect the signals that we're after and ensure that we know where the threshold is for a high significance detection. We also perform hardware injections. That is to say, we have light beams from lasers. We modulate their intensity. The photon pressure is enough to shake our mirrors. And in that way, and we can then measure the intensity of the light. And the greatest source of uncertainty actually is measuring the intensity of the light accurately. This is a real challenge, but never mind. We can then calibrate our instrument to within a few percent in terms of sensitivity, and of course check for things like phase and so forth. And in that way, determine that our instrument responds the way we think it should to an actual physical mirror motion. Of course, one of the things that we have to do is make sure that we don't fool ourselves by doing an accidental injection, either in software or in hardware, or it could be subject to a malicious injection. We did a very careful study of that, and we determined that that would not be possible. Well, we could, in fact, inject, by the way, binary black hole signals, and we do that regularly. We don't have enough force to inject a binary neutron star. At high frequencies, the inertia of the mass keeps the mass from moving, and so we don't even have a way to make an injection at high frequencies. So with all of that, we can claim success. We can form a histogram of the number of events versus detection statistic. And for our first detection, of course, it was a very clear, very clearly separated from all background that one might see. So let me draw back and now talk in a more general sense about where we are with looking at our data. We're still analyzing both O1 and O2 data. These are the 2 observing runs, the second one which ended some year or so ago. We're completing the search on the O2 data. We're completing a catalog of all of the events. Other searches, for instance, the continuous wave search for a rotating neutron star with, say, a 10 to the minus 6 asymmetry, that goes on. That takes a long time. It's very computationally intensive to correct for all Doppler shifts for all points in the sky. And per the data management plan, the strain data from the entire O2 run, the O1 data are already public. The entire strain data from the O2 run will be available to the general public in February of 2019. And we look forward to the independent analysis. Speaking of those kinds of analyses, let me mention again WASC, which is at this webpage here. You can find it by looking in Google if you want. There we host gravitational wave strain data, event localization in the form of sky maps, full data sets, tutorials, which, by the way, have toy approaches to analyzing the data. Those are not the ones that we use. And also more and more software links for our full data suite, our full software suite that we use for doing our own data analysis. And we intend for this to grow in scope. We're actually really pleased to see that people outside of the collaboration are working hard on understanding our data and either following our footsteps or taking different paths to looking at our data. We could hope that that will increase the confidence in what we see, will allow for searches for events the LVC didn't find, searches for hypothesized events for things that we have not yet thought of looking for. There are other talks in this conference on that sort of thing. And there's a growing list of papers that are appearing. Also, input from the community is helping us adjust on what we put up and helping us understand what we've done. We can thank Cresswell et al. For having found, for instance, that the display figure that we have for the difference, between the signal and the template that we put up for our first paper wasn't actually an accurate residual. That's not the one that we used for our data analysis. It was just a figure error. And then we're also adding posterior samples at the request of D et al., which is a sophisticated group of people who have left the collaborations, and they're looking for more detailed products. We're putting them up. It's just a snapshot of the page where papers are showing up on this matter. So what else have we seen? I can't dwell on this for too long. But one thing I want to mention is that we had the very happy happenstance shortly after Virgo joined the end of our O2 run, that we were able to see the first binary black hole with 3 detectors. Here you can see, for instance, at the bottom is the strain as a function of time for the 3 detectors, and along with the model signal that matches it best. And having 3 detectors allowed us to move from, I was referred to earlier today as the banana, of a relatively large uncertainty in the sky to a much smaller, let's call it peanut-shaped, which is enabled by having a 3rd instrument as part of the sky localization process. Oh, and that allowed us not only to reduce the angular size by some factor of 20, but also the volume. And it was noted earlier that this was really key to being able to do a lot of the physics that's been done and to find a host galaxy. Volume was reduced by some 34 times. How do we form that sky map? We treat the detectors as a phased array antenna. It's not just triangulation. It's not just time of arrival. We take into account the detailed antenna patterns for the 2 different polarizations of our gravitational wave antennas. And then we can effectively phase up the antennas to ask what would be what is the sensitivity in this direction, the sensitivity in this direction, and we look at the entire sky like that. It requires computers. We've got computers. So then let me move to just one last detection to mention. It's not the first time it's been talked about today, the binary neutron star that was seen on August 17th. And you can see this most clearly in this spectrogram of the Livingston site, where you see the long ramp up. We actually saw it for, 90 seconds or so. This just shows the end of the process and gives you an idea of what the signal looks like. One thing your eye may have noted is that the trace of the binary inspiral becomes faint at this point in the Livingston curve. Why is that? It's because there was a glitch in the Livingston data. The glitch itself actually was a very short period of time in the detector output, just some tens of milliseconds long, that was an electronic saturation of one of the D to A converters that keeps the masses in position. And that shows up in the spectrogram as this beautiful spike. Well, by providing a window function to reduce the amplitude at that, actually I should say a window function like this, to snip out the data at that time, we could go back to the data analysis procedure and include the data from Livingston to determine the exact time and other features of the data. The other thing that you may have noticed is that the trace doesn't seem to be visible in the Virgo detector. Why is that? Coming back to the antenna pattern again, here I show something which is actually an average of the 2 polarizations together. You can imagine if you have a signal from overhead, it can squeeze one arm and stretch the other arm. That gives you the highest sensitivity. If you come in from the side, the effect is all transverse to the beam. This arm doesn't change length at all, whereas this one is modulated. The antenna is a factor of 2 less sensitive for things from the side. If you actually come in at the vertex, you don't change the length of either arm. It's a point of 0 response in the system. It so happens that GW170817 was at that position, very close to it, for Virgo, and thus the signal was very hard to see, effectively impossible to see. But because of our aperture synthesis process, that doesn't harm the position detection at all. You say, it was a source which was at a position such that there was no signal in Virgo. That actually gives you additional information for where the source was. Very, very neat. So you've already seen this plot here. the gamma ray burst came just 1.7 seconds after what we call the end point of our in spiral. It's a wonderful chronology to walk through. I actually have something, an animation on the next page, which is a lot more fun way to do it in detail, so I won't walk through this. I'll just note that there were, it was indeed the GRB trigger that was the first thing that the Earth learned about this, this passing event, and it took us about 6 minutes before we had passed all of those hundreds of thousands of templates over our data to discover that we also had a signal. And then we put those two things together and got very excited. We worked as hard and as quickly as we could to perform the synthesis of a sky map. It was still daytime in Chile. A bunch of teams went to work to plan their plot for what sources they would look at. And effectively, as soon as the sun set, the host galaxy was found. Here's a really nice animation. I think it probably comes from NASA on how this worked. Fermi was the first to see. The integral satellite followed shortly thereafter, so that now the gamma rays located the signal to a section of a circle. Shortly thereafter, we had the actual detection, which took place in the two LIGO instruments, providing 2 bananas for the localization. But then we brought in the Virgo data, and that shrunk it down to the size that was sensible for astronomers to look. We sent that to the astronomers. They immediately picked out those galaxies that were within the field of view, and then I think it only took, I don't know, but tens of minutes or something like that to narrow in on NGC 9. Well, I can't actually remember the number of it, I'm embarrassed to say, but to settle in on the host galaxy and to identify it, send out coordinates, and everybody else got to work. Just a really fun moment. I don't need to say anything more about this slide. This is possible because there are thousands of people working together. The LIGO scientific collaboration and Virgo collaboration is in fact about 1,500 persons, 120 institutions, 21 countries, and we work in a very coherent way to build the machinery to make this happen and then to exploit the data that come from it. So what does the future hold? The next thing is up is the O3 observing run. It's going to start in something like February of 2019. It'll last about 1 year. I think the thing to jump to here is to note that we expect the network to be something like a factor of 2 better. Cube that if you want to know what the rates might be. And those rates turn out to be probably a few per month for binary black holes, perhaps as many as once per week. For binary neutron stars, we could expect between 1 to 10 in the period of a year, kind of once a month, if we're optimistic. We would really like to see a neutron star binary black hole, or a binary made up of a neutron star and a black hole, because that should illuminate much more clearly the tidal forces. Once O3 is running, we've changed our mode so that we will be emitting open public alerts. They're no longer a question of writing an MOU with LIGO or with Virgo to be able to have access to the data. So all observers everywhere, people in their backyards, can subscribe to these and try to find new items in the sky. We're hoping that the preliminary alerts will be out as quickly as a few minutes after the event passes by the system, 10 minutes or something like that. It's clear that the earlier you can get to these sources, the more you can learn from them. Then further on the horizon is A+. This is a modest upgrade to the advanced LIGO system. We expect that to come onto line somewhere around 2024 or so, and there'll be another range of, say, another factor of 4 to 7, depending upon the kind of source, in the rate that we can imagine for gravitational waves. Now, we actually have plans that are further out into the future. That's some of the stuff that Yo will be talking about tomorrow in his talk. I hope you'll be able to listen to that, because the two talks really form together a whole. And with that, oh, phooey. Actually, how do I do this? I don't think I can get to it. Oh, I think I can. I just want to say that return. Yeah, good. So we have a bright future in front of us. We have the two LIGO detectors and the Virgo detectors, which have been active so far. The Kagura detector, and there have been a number of talks at this conference about that, the Japanese detector, may be able to join us for the end of the 03 observing run. LIGO India is well on its way. India is building an infrastructure that will house a third LIGO detector that's already built and sitting in storage up in Hanford, Washington. And I think we'll have a very bright future for what's going to happen in gravitational waves and the rest of the astronomical world. So, thank you. Yeah, and so to repeat the question, for the first detection that I went through, you could see very clearly the signal in the time series just with some high and low pass filtering. In the case of the binary neutron star, that's not possible. And it's interesting because, in fact, the detection confidence for the binary neutron star is even higher than it was for that first detection. The difference is that our first signal only lasted for fractions of a second, whereas the binary neutron star was seen for a minute and a half. We were able to accumulate phase and to match our template over that very long period of time, and in that way have extremely high confidence that we'd found not only a signal, yes or no, but also what the parameters of that signal was. And in fact, for us, the shock was the first detection. All of our pipelines and our processes for filtering the data, processing the data, are posited on the idea that signals are going to be hard to find. Sometimes we find easy to find signals. Most of them will be hard to find and will be of this ilk where there's nothing to see, perhaps even in a spectrogram, but these processes of doing optimal filtering and the processing of the data will allow us to pull out the signals with high confidence. Okay, I'm a bit hard of hearing and the acoustics are not great. One more time, please.
When you feed the data
Yes.
using the X-ray spectrum, you generally get from 5 to 15 solar masses as the stellar mass black holes. But unfortunately, all the cases that you have fitted, all random numbers like 23, 36, which never, out of all the X-rays that we have, sources we have seen, maybe 30 or so, all of them are, let us say, below 15. But in your case, all of them are above 23, 36. So, and then they say, okay, we have a way to make them. That is not the issue. Issue is, why didn't you see the lower mass black holes in the first place? Are you ignoring the spin, or is there a problem with the data analysis?
Okay, so if I understand, it appears that there's a selection effect that's causing us to see a range of black holes, which does not include the binary black holes that have been seen, say, with X-rays or so. So there are a couple of things that are, I think the most significant thing that's at play here is that the size of the signal scales with the size of the mass. And so larger masses are easier for us to detect. And I think that as we go further into our observing runs, we'll see more and more a distribution of masses. In fact, we have more events that we have not yet published. And I think that we'll see that there's more of a continuum of masses. There may be, in fact, a real spectrum to the masses. There may be many more at high mass, or there may be a bulge at some point, and that sort of spectroscopy or butterfly collecting of black holes may give us deeper insights into the formation of the black holes. But all it can do is report the masses which match the templates that we have to date. Thank you. Which people should be mentioned when we talk about the history? I can only speak for the experimental detection, of course. I mean, obviously, Einstein was a very important point of departure. The first persons that I know who mentioned the idea of interferometric detection were Gerstenstein and Pustervoit, who published in JETP back in, I think, the 50s or thereabouts, the idea, the concept of using that. There were a number of early mentions of using interferometers. Even Joe Weber, who thought of the idea of the excited cylinders, wrote in his lab notebook, maybe we should try an interferometer with this. The person whom I see, he was my mentor, so maybe I'm biased, the person I see as really the key individual here was Ray Weiss, who independently reinvented the interferometer. Wasn't the first, wasn't the last, but he laid out in 1972 the steps that we needed to follow for the decades that followed to actually build instruments that would work. He talked about the thermal noise, the shot noise, the seismic noise, all of the various different, the frequency noise, the amplitude noise, the isolation problems. He had it all mapped out for us, and then he stuck with it. So I would call him certainly extremely important. Then we have a Nobel Prize to account for. Kip Thorne, who was extremely important in putting on a solid basis the notion of reasonable sources connecting us with the astrophysics. And Barry Barish, it's also, again, the discipline that I've followed. It takes a lot of people working together in a coherent way to make these things happen. People who make people work together are crucial for big science. Barry Barish did that for us. So those three people actually played important roles. I could go on and on, Stan Whitcomb, and I'll stop there, though. Thank you.
Felix?
Please do. Do you want to take the microphone?
Just a comment on the difference in masses between the black holes detected by gravitational waves and those detected by X-ray studies. The ones that we see in the X-ray studies are in our galaxy or in nearby galaxies. And the black holes, the progenitors of those black holes in X-ray studies are probably very rich from the chemical point of view, whereas the black holes that you are detecting in gravitational waves were formed very early from progenitors that had very low metallicity. So progenitors with high metallicity lose a lot of mass in their evolution. So the core of the star that will be formed, and then the black hole out of that core should be more massive, because those stars do not lose that much mass as the ones with low metallicity.
Thank you. I will admit I'm an instrument builder, and I'm learning about the astrophysics, and now you've taught me something. Thank you.
There was a suggestion that the binary black hole was lensed. Do you have any comments on that suggestion?
And that's because it was thought perhaps that we saw two images come, or I don't know. I think, again, I'll plead some ignorance, again, because I'm not a specialist in the astrophysics. I don't think that we've seen anything complicated in the signals that we've recovered that force us to choose a more complicated signal model than a simple direct detection. It would be wonderful, for instance, to see a signal and to see a delayed version of it for two different paths around a lensing, or some other effect that could be interpreted as something along the path. But I don't know of any data that we have that would allow us to conclude that.
There is amplification bias, which makes...
And that could push things around. It's true. It's true. As we gain more and more signals, perhaps we'll be able to form some statistical vision of the signal strengths and the kinds of masses we see. And you'll have to tell me if we should stop this.
You say
David, could the LIGO see the signal without using prior information before the matching filtering? On the stage of coherent web analysis, so we have six events at the moment now. So at least all of them could be seen without this prior information, only part.
It's been a wonderful thing that we've had signals that have been so strong. That certainly won't be the case for all. It was, of course, a gift that the first signal was so strong that it could be seen without a lot of fancy machinery. Obviously, if you then want to extract parameters, you have to make some assumptions about the source, assume general relativity, and so forth and so on. No assumptions have been needed for a number of our sources, and that gives a lot of confidence, I think.
think that this was the last question. We had more questions because he saved some time his speech. I would thank him again.